Welcome to our channel. We are so glad you found your way here. Let us help you fall asleep. Let's begin with planetary tides, how gravity shapes the surfaces of moons. Take a slow, deep breath in and release it. Let the weight of the day fade away as we embark on an unhurried, atmospheric journey through the wonders of the cosmos. Your mind is quiet, the universe is vast, and we are ready to explore. The interaction between celestial bodies creates a delicate balance, one that dictates the movements and characteristics of moons. Tidal forces arise from gravitational gradients, where the strength of gravity varies across an object. This phenomenon is particularly evident in regions where a moon orbits a planet, leading to the stretching and compression of its surface. These forces generate significant internal friction, resulting in the heating of the moon's material. The gravitational pull of a nearby planet exerts pressure on the moon's surface, altering its geology and leading to geological phenomena such as volcanic activity and tectonic shifts. For instance, the intense tidal forces experienced by certain moons can contribute to an environment where liquid subsurface oceans exist, supporting the potential for life. Variations in orbital eccentricity further amplify these tidal effects, producing a dynamic interplay that shapes the moon's surface over time. The gravitational influence of companion moons or nearby planets can also modify these forces, creating complex gravitational interactions. The principles of gravity, as first articulated by Sir Isaac Newton in the 17th century, describe this force as a mutual attraction between masses. This foundational concept underscores the dynamics of celestial bodies, elucidating how larger entities exert force on smaller objects. Newton's law of universal gravitation posits that the strength of this attraction diminishes with distance, illustrating the delicate balance governing the motions of moons and planets. Albert Einstein expanded upon these ideas in the early 20th century with his theory of general relativity. This framework redefined gravity not merely as a force, but as a curvature of space-time caused by mass. In this view, celestial bodies follow the contours of this curvature, leading to complex orbital patterns. The implications for moons are significant. Their surfaces are shaped by the gravitational pull from their parent planets and the intricate dance of other nearby celestial entities. In these interactions, tidal forces emerge, influencing geological activity and surface characteristics. The intense gravitational tugging can result in phenomena such as volcanic activity or tectonic shifts, which profoundly alter the landscape. Each moon, subject to its unique gravitational environment, showcases the diverse effects of these fundamental principles, revealing the intricate relationships at play across the cosmos. Understanding these interactions provides insights into the evolution and characteristics of celestial bodies throughout the universe. The role of tides extends beyond mere surface alterations, influencing the overall dynamics of celestial mechanics. Gravitational forces exerted by massive bodies create varying tidal effects, leading to complex orbital behaviors. This phenomenon is particularly evident in systems where moons engage in synchronous rotation, maintaining a fixed orientation towards their parent planet. Such alignment results from tidal locking, a process dictated by gravitational interactions over extensive periods. Variations in tidal forces can induce internal heating, affecting geological activity. This heating occurs as the materials within a moon respond to the flexing caused by gravitational pull. The release of energy may contribute to the presence of subsurface oceans, as seen in icy bodies like Europa and Enceladus, where liquid water exists beneath a frozen crust. In addition to geophysical changes, tides influence the orbital stability of moons and planets. The transfer of angular momentum between a planet and its satellite can lead to gradual changes in their respective orbits. Over time, these alterations can result in significant shifts in distance and rotational dynamics. Celestial mechanics, driven by tidal forces, shapes the intricate relationships between moons and their planets, highlighting the delicate balance of gravitational interactions that govern their existence. This interplay creates a unique environment conducive to the exploration of potential habitability beyond Earth. Tidal forces arise from the gravitational influence exerted by celestial bodies on one another. This effect is particularly pronounced when the mass of one body, such as a planet, significantly outweighs that of its satellite. The gravitational pull varies depending on the distance between the two objects, leading to variations in force across the surface of the smaller body. Areas closer to the larger body experience a stronger pull, while those farther away feel a weaker influence. Gravitational forces, on the other hand, are a fundamental aspect of physics, describing the attraction between two masses. This attraction governs not only the motion of celestial bodies within a solar system, but also influences the trajectories of comets and asteroids that venture through the cosmos. The distinction between tidal and gravitational forces is crucial in understanding the geophysical processes on moons. Tidal forces can induce significant internal friction, generating heat within the moon's interior. This heat can drive geological activity, leading to phenomena such as cryovolcanism or tectonic movement. In some instances, a moon may experience tidal locking, where its rotational period synchronizes with its orbit around a planet. This results in one hemisphere perpetually facing the planet, while the other remains in darkness, shaping the unique climatic and geological features of its surface. Early theories of gravity provided foundational insights into the relationship between celestial bodies. Observations made by ancient astronomers suggested that the movements of the moon and planets were not mere coincidences, but rather governed by underlying forces. Philosophers, such as Aristotle, posited that celestial spheres were perfect and immutable, yet they lacked explanations for the observable phenomena. With the advent of the scientific revolution, figures like Galileo began to challenge traditional views, laying the groundwork for a more empirical approach to understanding motion in the cosmos. The notion of gravity was further developed by Isaac Newton, who articulated the universal law of gravitation in the late 17th century. His work elucidated how the gravitational attraction between bodies could explain not only the orbits of planets, but also the tidal forces exerted by larger bodies like Earth and its moon. These insights revealed that the gravitational pull of a planet could induce significant tidal forces on a moon, affecting its geological characteristics over time. The cyclical nature of these forces contributed to the erosion and reshaping of surfaces, leading to the formation of unique geological features. This understanding marked a pivotal shift in how humanity comprehended the dynamic interactions between celestial bodies, setting the stage for modern studies of planetary science and astrophysics. The influence of the moon on Earth's tides exemplifies the intricate gravitational relationships within our solar system. Each lunar cycle brings a rhythmic rise and fall of ocean levels, a direct consequence of the moon's gravitational pull. This phenomenon occurs as the moon orbits Earth, creating bulges in water that manifest as high tides. Conversely, areas perpendicular to the moon experience low tides, resulting in a predictable pattern across the globe. This oscillation is not merely a local occurrence. It affects coastal ecosystems, shaping the environments in which myriad species thrive. The tidal forces contribute to nutrient distribution, influencing the feeding and breeding cycles of marine life. These interactions showcase a delicate balance, where gravitational forces orchestrate ecological dynamics. Further examination reveals the subtle variations in tidal patterns influenced by the Earth's rotation and the elliptical nature of the moon's orbit. This complexity results in semi-diurnal and diurnal tides, creating diverse tidal experiences in different geographical locations. The interplay between the moon's gravitational effects and the Earth's land masses introduces additional variables, leading to unique tidal phenomena observed in bays and estuaries. Understanding these interactions enhances knowledge of Earth's systems and their responses to external forces, providing insights into both the present and future of our planet's climate and ecosystems. The Earth-Moon system serves as a prime example of tidal locking, a phenomenon wherein a celestial body's rotation period matches its orbital period around another body. This results in one hemisphere of the moon perpetually facing Earth, while the opposite side remains hidden from view. The gravitational forces exerted by Earth have gradually synchronized the moon's rotation, a process that has unfolded over millions of years. The implications of this tidal locking extend beyond mere alignment. The shared gravitational relationship has led to significant geological and atmospheric consequences on both bodies. On the moon, the constant face toward Earth has resulted in uneven surface features, with the near side showcasing vast lunar maria formed by ancient volcanic activity, while the far side remains more rugged and densely cratered. This disparity highlights the long-term effects of gravitational interactions. Earth, in turn, experiences a stabilizing effect from the moon's presence. The gravitational pull contributes to maintaining a relatively stable axial tilt, which influences seasonal variations and climate patterns over geological timescales. As the moon continues its slow drift away from Earth, approximately 3.8 centimeters annually, the impact of this tidal locking will evolve, potentially altering the dynamics of both celestial bodies in the distant future. As these changes unfold, they will provide crucial data for understanding planetary evolution and habitability. The concept of synchronous rotation reveals a fascinating aspect of celestial mechanics. Some moons exhibit a unique relationship with their parent planets, rotating on their axes in perfect synchrony with their orbital period. This phenomenon results in one hemisphere perpetually facing the planet, while the opposite side remains hidden from view. The gravitational pull exerted by the planet creates substantial tidal forces, shaping the surface of these moons over time. The constant tug of gravity results in a variety of geological features, from vast plains to towering mountains, all influenced by the relentless pressure of their parent bodies. This region, where tidal flexing occurs, experiences significant internal heating. Such heating can lead to geological activity, including volcanic eruptions and the potential for subsurface oceans. These dynamic environments foster conditions that may allow for the development of life. The hidden hemisphere, often cloaked in mystery, may harbor unique characteristics, shaped by the intricate balance between gravitational forces and the Moon's geological processes. Understanding synchronous rotation is paramount for unraveling the histories of these moons. It provides insights into their formation and evolution, revealing how they have been sculpted by the relentless forces of their larger counterparts. The ongoing study of these celestial bodies continues to shed light on the complex interplay between gravity and the surfaces of moons throughout the solar system. Telescopes have unveiled remarkable details regarding the effects of tidal forces on various moons. Observations reveal that gravitational interactions between moons and their parent planets lead to significant geological activity. This region surrounding the gas giants, particularly, displays moons exhibiting vast surface variations, indicative of ongoing tectonic processes. Measurements taken by space-based observatories show that some surfaces are marked by deep fissures and extensive mountain ranges. These features hint at the internal heating caused by the gravitational pull of nearby celestial bodies. For instance, detailed imaging of Europa illustrates a cracked ice shell under which a subsurface ocean may exist, sustained by the warmth generated through tidal flexing. The incessant tug-of-war between a moon and its planet creates an environment ripe for unique geological phenomena. Observations have also identified cryovolcanoes, which erupt with icy materials rather than molten rock, providing a glimpse into the dynamic processes at play. This phenomenon is particularly evident on Enceladus, where geysers expel water vapor and organic compounds, hinting at an active subsurface ocean. In addition, measurements of orbital eccentricity provide insights into how gravitational forces shape orbits, further influencing surface features. Each discovery adds another layer to our understanding of how these gravitational interactions sculpt the very fabric of these distant worlds. Orbital eccentricity plays a crucial role in the dynamics of tidal forces. Variations in the shape of an orbit influence the strength and nature of gravitational interactions. In elliptical orbits, the distance between a moon and its planet fluctuates, leading to periodic changes in tidal forces. At periapsis, when the moon is closest, gravitational pull intensifies, resulting in pronounced tidal bulges. The effects are less pronounced at apoapsis, where the moon is furthest from its host. This cyclical variation in distance leads to differential tidal heating for moons with significant eccentricity, such as Io and Europa. The constant stretching and flexing generates substantial internal heat. The process contributes to geological activity, creating volcanic eruptions and subsurface oceans. This heating mechanism can sustain environments conducive to life. Some moons experience even greater tidal forces due to resonance with neighboring bodies. These gravitational relationships further amplify eccentricity, enhancing tidal effects. Over time, such interactions can lead to orbital stabilization or migration, altering the evolutionary trajectory of these celestial bodies. The surface features of moons bear testimony to these dynamic processes. Craters, ridges, and fractures tell the story of an ever-changing landscape shaped by the relentless pull of gravity. Each surface characteristic offers insight into the intricate balance between celestial mechanics and geological activity. Tidal heating arises from the gravitational interactions between a celestial body and its parent planet, an effect that generates internal friction and warmth. This phenomenon is particularly pronounced in moons orbiting massive planets, where variations in gravitational pull induce deformation. As these moons experience this stretching and flexing, their interiors heat up, leading to dynamic geological processes. This heating can manifest in various forms, from volcanic eruptions to the presence of subsurface oceans. For instance, the icy crust of Europa conceals a potentially vast ocean beneath its surface, warmed by the energy produced from tidal forces. The implications of such environments extend beyond mere geological interest. They raise questions about the potential for life in these hidden realms. In contrast, moons like Io exhibit extreme volcanic activity as a direct consequence of tidal heating. The constant gravitational tug-of-war with Jupiter shapes a landscape marked by active lava flows and sulfuric plumes. This constant reshaping highlights the profound influence of gravitational interactions on surface morphology. Research into tidal heating not only enhances understanding of these moons, but also informs broader discussions about planetary formation and evolution. These mechanisms reveal the interconnectedness of celestial bodies, underscoring how gravity orchestrates complex processes within the cosmos. The study of these interactions continues to offer new perspectives on the nature of our solar system. Tidal forces exerted on the Galilean moons illustrate the profound impact of gravitational interactions within this region. Ios, the innermost of the Ford, experiences the most intense tidal heating due to its proximity to Jupiter. The constant flexing of its surface results in volcanic activity, making it the most geologically active body in the solar system. This relentless energy reshapes its landscape, creating vast lava plains and towering volcanoes. Europa, slightly farther out, possesses a subsurface ocean beneath its icy crust. Tidal forces here maintain the liquid state of this ocean, generating an environment potentially suitable for life. The interaction between the moon's icy exterior and its ocean hints at the complexities of habitability in extreme conditions. Ganymede, the largest moon in the solar system, exhibits a different geological history. While it also experiences tidal flexing, the effects are less pronounced compared to Io and Europa. The intricate interplay of tectonic processes has produced a diverse surface featuring both ancient and young terrain. Callisto, the outermost moon, experiences the least tidal influence. Its heavily cratered surface suggests a lack of geological activity over billions of years. The contrasts among these four moons highlight the variability of tidal effects and their implications for both geology and potential astrobiology within this unique system. Liquid oceans exist beneath the icy crusts of these moons, sustained by tidal forces exerted by their parent planets. The gravitational pull creates friction within the subsurface, generating heat that prevents the water from freezing solid. This phenomenon leads to the maintenance of vast sailing bodies, which are crucial for astrobiological prospects. In this region, Enceladus stands out, with geysers that erupt from its surface, releasing plumes rich in water vapor and organic compounds. These eruptions suggest a dynamic subsurface ocean, continuously interacting with the icy shell above. This interaction may create conditions conducive to life, as hydrothermal vents on the ocean floor could provide essential nutrients. Europa, another noteworthy moon, bears a similarly intriguing ocean beneath its ice. The surface is marked by ridges and chaotic terrains, indicative of a constantly shifting icy crust under which vast liquid water exists. The exchange between the ocean and the surface is essential, allowing for the circulation of chemical elements that may foster life. Titan, with its dense atmosphere and lakes of methane on the surface, presents an alternate case. Below its thick haze lies a liquid ocean of water, kept warm by tidal heating. suggesting a complex interaction between known and exotic chemistry. These unique environments collectively illustrate the profound influence of tidal forces on the potential for life beyond Earth. Tidal forces exert significant influence on geological activity, shaping the surfaces of moons in remarkable ways. The gravitational pull from a nearby planet creates continuous flexing within the moon's interior. This process generates heat through friction, leading to volcanic activity and tectonic movement. Such phenomena are evident on celestial bodies like Io, where the intense tidal forces result in the most geologically active landscape in the solar system. This activity manifests as continuous eruptions, producing plumes of sulfur and other materials that contribute to a dynamic atmosphere. The heat generated from these forces also affects subsurface oceans, creating environments where chemical reactions may support microbial life. The interaction between the solid crust and the liquid interior establishes a delicate balance, fostering a rich geological environment. In contrast, moons affected by less intense tidal forces exhibit a more stable geological state. These bodies may present a surface covered in ancient craters, reflecting a history of minimal geological change. The variation in tidal influence underscores the diversity of geological processes at play across different celestial bodies. Understanding these interactions enhances our knowledge of planetary formation and evolution. Each moon, sculpted by the consistent pull of its parent planet, reveals vital clues about the conditions necessary for life and the complex interplay between gravity and geological activity. Resonance plays a crucial role in shaping these tidal interactions. When multiple celestial bodies exert their gravitational influences, they can enter resonant orbits, amplifying the effects of tidal forces. This phenomenon occurs when their orbital periods are related by a ratio of small integers, causing them to experience gravitational tugging at regular intervals. Such interactions can lead to significant variations in tidal forces, resulting in geological activity that reshapes surfaces over time. A prime example can be observed with the Galilean moons of Jupiter, Io, Europa, and Ganymede, are ensnared in a gravitational tug-of-war. Their orbits locked in a 3:2:1 resonance. This alignment generates immense tidal forces, especially on Io, where volcanic activity is rampant, driven by the constant flexing of its interior. The energy produced by these interactions results in a surface marked by extensive lava flows and sulfuric plumes. Europa, in contrast, remains relatively smooth, its icy crust hinting at a subsurface ocean beneath. The gravitational pull from its larger neighbor induces stress on its surface, creating cracks and ridges that suggest a dynamic environment. These resonant relationships highlight the intricate balance of forces at play, revealing not only the geological diversity of moons, but also the potential for habitability in environments shaped by such complex interactions. Tidal forces exert a profound influence on the formation and maintenance of planetary rings. The gravitational interactions between a planet and its moons create a dynamic environment where material is continuously shaped and reshaped. This region, often characterized by a delicate equilibrium, is home to countless particles, ranging in size from minute grains to larger boulders. These remnants of past celestial events coalesce into a striking structure that encircles the planet. When moons venture too close to their parent planet, they may encounter the Roche limit, a threshold where the planet's gravitational pull exceeds the self-gravity of the moon. This condition leads to the disintegration of the moon, resulting in a cascade of debris that contributes to the formation of rings. In this way, the remnants of moons provide insights into the historical processes that shaped these ring systems. The composition of rings varies significantly, influenced by the surrounding environment and the source of the material. Icy particles reflect sunlight, creating a brilliant spectacle, while rocky fragments absorb it, resulting in a dimmer appearance. Dust and ice coexist in a complex arrangement, with gravitational forces continuously adjusting their position.
The intricate structure of these rings is further sculpted by the gravitational influence of nearby moons, demonstrating an ongoing interplay of forces that shapes this mesmerizing feature of planetary systems. The dynamic forces exerted by their parent planets have profound implications on the atmospheres of moons. Tidal forces induce significant stress, leading to geological activity that can result in the release of gases and volatiles. This phenomenon contributes to the thin atmospheres observed on some of these celestial bodies, where the balance between gravity and atmospheric pressure is delicately maintained. Variations in gravitational pull can cause surface deformation, generating heat through friction. This heat may play a crucial role in maintaining subsurface oceans, as seen on moons such as Europa and Enceladus. These hidden reservoirs of liquid water potentially harbor conditions suitable for life, highlighting the importance of tidal heating in shaping both surface and atmospheric dynamics. The atmospheric composition of moons can also be influenced by the interaction of solar radiation with surface materials. When combined with the effects of tidal forces, this can create a complex environment where gases escape into space while others are replenished through geological processes. Volcanic activity, spurred by tidal heating, can further enrich the atmosphere with particulates and gases. Observations of these moons reveal variations in their atmospheres that reflect the intricate balance between internal and external forces. The ongoing evolution of these moons illustrates the subtle yet powerful influence of gravitational interactions in the broader context of planetary systems. Tidal forces play a crucial role in planetary differentiation, shaping both the internal structure and surface features of moons. This process begins with the gravitational pull exerted by a parent planet, which creates variations in the density and composition of the moon's material. These forces lead to the heating of the moon's interior, causing the migration of materials towards the core and the subsequent formation of distinct layers. Crucial to this differentiation is the concept of tidal heating, which arises from the constant flexing of a moon's body as it orbits its planet. The friction generated by this flexing results in the melting of ice and rock, allowing for geological activity. In extreme cases, such as with Io, one of Jupiter's moons, this heating can drive intense volcanic activity, reshaping the surface and contributing to a dynamic landscape. Surface features are often a direct result of these tidal influences. Craters may appear elongated, or fault lines may develop, indicating the internal stresses imposed by gravitational interactions. As moons experience varying tidal forces over millions of years, their surfaces evolve into complex terrains, reflecting their unique histories. The intricate interplay between tidal forces and geological processes provides insights into the formation and evolution of these celestial bodies, illustrating the profound impact of gravity on their development. Tidal forces exert pressure on these surfaces, leading to crustal deformation that can manifest in various geological features. This constant flexing and stretching can result in the formation of ridges, fractures, and even cryovolcanoes. Such phenomena indicate a dynamic interior, often fueled by the heat generated from gravitational interactions. Geophysical studies highlight the significance of these processes, revealing how they contribute to the thermal evolution of moons. In regions where tidal heating is pronounced, the surface often displays signs of recent activity. These areas may lack impact craters, suggesting a relatively young geological age. Observations from spacecraft missions have provided data revealing the extent of this deformation, showcasing how it varies between different moons. For instance, certain icy satellites exhibit smooth plains, while others are characterized by rugged terrains and chaotic surface features, each telling a story of their unique gravitational histories. The study of tidal forces extends beyond mere observation. It combines satellite data with simulations to model the internal structure of these bodies. This modeling aids in predicting future geological activity, offering potential insights into their habitability. Understanding these processes not only illuminates the past, but also shapes future explorations, guiding scientists in their quest to comprehend the complexities of our solar system's diverse moons. Measuring tidal forces involves a combination of satellite and ground-based observations that allow scientists to gather intricate data about gravitational interactions. In this region, satellites equipped with advanced sensors orbit celestial bodies, capturing essential information about their surfaces and gravitational fields. These instruments measure minute changes in distance and gravitational pull, offering insights into the forces exerted by nearby planets and the resulting tidal effects. Ground-based observatories contribute significantly by monitoring the moons in various wavelengths, enhancing our understanding of surface changes over time. By analyzing images taken from Earth, researchers can detect variations in topography and surface composition, which are influenced by gravitational interactions. This multifaceted approach ensures a comprehensive understanding of tidal forces. The gravitational interplay leads to phenomena such as tidal heating, which can drive geological activity. Such activity might manifest as surface deformation or even volcanic eruptions, creating a dynamic landscape that evolves continuously. This evolution can be tracked through long-term observations, revealing patterns that signify the underlying processes at work. Data collected from both satellite and ground-based sources are then synthesized, allowing for models that predict future behavior of these celestial bodies. This ongoing research not only deepens the understanding of tidal forces, but also informs missions aimed at exploring these moons. The influence of distance on tidal strength plays a crucial role in shaping the surfaces of moons. Gravitational forces diminish with increasing separation, leading to variations in tidal effects across different celestial bodies. For example, a moon situated close to its planet experiences more intense tidal flexing than one orbiting at a greater distance. This phenomenon is particularly evident in the relationship between Jupiter and its myriad of moons. The closer moons, such as Io, endure extreme tidal heating due to Jupiter's massive gravitational pull, resulting in a geologically active surface marked by volcanoes and sulfuric plumes. In contrast, moons farther away, like Callisto, exhibit significantly less tidal influence. The resulting surface is comparatively stable, with fewer geological changes over time. Surface features, such as craters and ice formations, remain largely unaltered, providing a stark juxtaposition to their inner counterparts. The gravitational interactions within this system lead to complex orbital resonances, further amplifying tidal effects on closely orbiting moons. These resonances can create a feedback loop, enhancing geological activity in some cases while suppressing it in others. The study of these tidal dynamics reveals essential insights into the evolution of moons, helping to understand not just their current state, but also their historical development and potential for harboring life beneath icy shells. The influence of multiple gravitational forces complicates the tidal interactions experienced by moons. It creates a ballet of gravitational pulls that shape their surfaces in intricate ways. Each moon is subject to the gravitational tug of its parent planet, while simultaneously being affected by the gravitational fields of nearby celestial bodies, such as neighboring moons or distant planets. This interplay generates a complex system of tidal forces that can lead to varying degrees of deformation. The variations in gravitational influence can result in significant geological activity. Some moons exhibit surface features indicative of tectonic processes, driven by the constant flexing and relaxation of their icy exteriors. The strain induced by these gravitational interactions can create fissures, ridges, and even cryovolcanoes, which may allow subsurface oceans to emerge, fostering potential habitats for microbial life. Consider the case of a moon orbiting a giant planet. The tidal forces from the planet may be enhanced or mitigated by the presence of other moons. This dynamic can lead to variations in heat generation within the moon's interior. Such thermal activity could maintain liquid water beneath a thick crust, opening avenues for astrobiological exploration. As scientists analyze these complex gravitational systems, they uncover the delicate balance that governs the evolution of moons, revealing secrets of their geological histories and the possibilities of life in the shadows of their icy surfaces.
Triton, Neptune's largest moon, presents a compelling case study in the influence of tidal forces within the outer solar system. This icy body exhibits a retrograde orbit, suggesting a history marked by gravitational interactions that have shaped its present state. The pull from its parent planet creates significant tidal heating, a process where gravitational forces cause internal friction,
thereby warming the subsurface. Surface features exhibit a diverse array of geological formations, including cryovolcanoes that hint at active internal processes. The presence of nitrogen geysers erupting from beneath a frozen crust reflects the dynamic nature of this moon. Such phenomena invite speculation about the existence of a subsurface ocean, potentially harboring organic compounds crucial for life. Weathervations indicate a surface rich in complex organic molecules, which could serve as precursors to biological activity. The interplay between Triton's atmosphere and its icy surface further illustrates the delicate balance of conditions that may support life. Analyzing these interactions reveals the intricate web of processes at work, sculpting the moon's landscape and influencing its atmospheric composition. Understanding Triton enhances knowledge of other celestial bodies within the outer solar system. Each moon, influenced by its planetary companion, a phenozone, contributes to a greater comprehension of tidal dynamics and the potential for habitability in these distant realms. Tidal forces exert significant influence on the geological and atmospheric characteristics of moons, creating environments that may foster life. These forces arise from gravitational interactions, which cause intense stretching and compression of the moon's surface. This process generates internal heat, potentially leading to volcanic activity. subsurface oceans, and other dynamic phenomena. The presence of liquid water, essential for life as known on Earth, may emerge beneath icy crusts, creating a habitat where biochemical processes can thrive. Regions experiencing tidal heating often exhibit geological features such as fissures and fractures, indicating active surface processes. These characteristics suggest not only the possibility of liquid water, but also nutrient cycling, which is crucial for sustaining life. Such environments can support extremophiles, organisms that thrive in extreme conditions, expanding the understanding of habitable zones beyond traditional models. Investigating these moons reveals a wealth of information about potential biosignatures, which may arise from microbial life. The interplay between tidal forces and geological activity creates a unique setting for astrobiological exploration.
Each moon serves as a laboratory, presenting varied conditions under which life could develop. These findings reshape the search for extraterrestrial life, suggesting avenues beyond familiar terrestrial environments. The implications for astrobiology are profound, inviting a deeper inquiry into the cosmos and its potential inhabitants. Tidal heating arises from the gravitational interactions between a celestial body and its parent planet, which induce internal friction and generate heat. This process plays a pivotal role in shaping the surface composition of moons. Variations in gravitational pull lead to deformation of the lunar material, resulting in a dynamic environment where geological processes can flourish. As heat builds up within these moons, it causes the subsurface ice to melt, transforming into liquid water in some instances. This alteration fosters a rich chemistry that can influence the surface features observed today. For example, the presence of geysers and cryovolcanoes on certain icy moons suggests that tidal heating may create a subsurface ocean, which could harbor organic compounds essential for life. Surface compositions of these celestial bodies exhibit a variety of materials, including complex hydrocarbons and salts, often a direct result of the interaction between heat and the icy exterior. The presence of these compounds indicates not only geophysical processes at play, but also hints at the moon's potential to support life, given the right conditions. Understanding the mechanisms behind tidal heating unveils the intricacies of planetary formation and evolution. Each moon presents a unique case study, revealing the varied outcomes of gravitational forces and their profound effects on surface characteristics. Tidal forces significantly influence cryovolcanism, a phenomenon observed on several icy moons. These gravitational interactions can cause the subsurface layers of ice to melt or deform, creating pockets of liquid water beneath the surface. This process is particularly pronounced in regions where the gravitational pull from a nearby planet or other celestial bodies generates stress on the moon's crust. Localized heating, resulting from the friction generated by this stress, may lead to the eruption of cryovolcanic material. This substance often consists of volatile compounds such as ammonia, methane, or water, which are expelled into space in a manner reminiscent of traditional volcanism. The eruptions can create surface features that vary in size and shape, contributing to the complex geological landscape of these moons. The cyclical nature of tidal forces results in a continuous reshaping of surface features, revealing the dynamic interplay between gravitational forces and geological activity. This relationship not only enhances our understanding of icy moons, but also provides insights into the broader mechanisms that govern celestial bodies within our solar system. The study of cryovolcanism offers a glimpse into the hidden processes beneath the icy crusts, showcasing how external forces can drive internal changes. These eruptions serve as markers of the ongoing evolution of these celestial bodies, reflecting the intricate balance of forces at play. Geophysical models of tidal heating reveal the mechanisms driving Io's remarkable volcanism. This moon, the most geologically active body in the solar system, exhibits a surface marked by countless lava flows and vast plains, sculpted by processes deeply rooted in gravitational interactions. The intense tidal forces exerted by Jupiter, combined with the gravitational pull of neighboring moons, create a complex interplay that generates immense heat within its interior. These interactions cause significant flexing in Io's crust, leading to the melting of silicate rock. Models suggest that the heat produced is not uniform, rather, it varies across the moon's surface, resulting in localized volcanic activity. This uneven heating contributes to the formation of extensive lava lakes and fiery eruptions, which can occur at intervals as brief as a few days. The release of sulfur and other materials during these eruptions contributes to the moon's thin atmosphere and colorful surface features, which include sulfur dioxide frost and vibrant volcanic deposits. Understanding the depth of tidal heating requires analyzing Io's orbital eccentricity, a byproduct of gravitational interactions with its fellow Galilean moons. This eccentricity leads to variations in distance from Jupiter, which in turn influences the magnitude of tidal forces acting on it. The continuous cycle of heating and cooling perpetuates an environment ripe for geological transformation. The gravitational interactions of celestial bodies dictate the dynamic evolution of their orbits, contributing to long-term stability. This region, where moons tread the delicate balance between their parent planets and neighboring satellites, experiences profound changes over eons. Variations in orbital parameters lead to fluctuations in tidal forces, which in turn affect surface features and internal structures. As these gravitational forces exert influence, the orbits of moons gradually adjust, often becoming more circular over extensive periods. This process involves the dissipation of energy through tidal heating, which maintains a state of geological activity. Over time, it can lead to the development of atmospheres or the emergence of subsurface oceans. Each moon exhibits unique characteristics, shaped by the specific gravitational interactions it endures. In cases where moons are engaged in resonant orbits, the interplay between them can amplify tidal forces, resulting in enhanced geological activity. These interactions foster an environment where internal heat is maintained, leading to the possibility of life in some cases. The gradual evolution of these orbits reveals a remarkable stability that belies the chaotic dance of gravitational forces. Long-term observations indicate that as moons continue to interact with their planetary systems, they may eventually reach a state of dynamic equilibrium, balancing gravitational pulls and internal processes. Tidal forces exert profound influences on the formation and evolution of moons. These interactions shape not only the surfaces but also the internal structures of these celestial bodies. Variations in gravitational pull lead to the heating of materials within moons, resulting in geological activity over extended periods. The interplay between tidal forces and the physical characteristics of moons creates an environment where differentiation of materials can occur, allowing for the stratification of surfaces. Theories of moon formation are diverse, yet they converge on the significance of gravity in these processes. Some suggest that moons can be captured remnants of larger bodies, while others propose that they form from the debris left behind after planetary collisions. In each scenario, tidal forces play a crucial role in stabilizing or altering the resulting orbits and rotations. These gravitational interactions can lead to significant surface features, such as the elongated shapes of certain irregular moons. This region exhibited signs of past geological activity, including impact craters and tectonic features that bear witness to their tumultuous histories. Continuous tidal flexing can generate heat, allowing subsurface oceans to exist, fostering the potential for life in the cold reaches of space. Such findings underscore the intricate relationship between gravity and the fate of moons in the vast expanse of the cosmos. Understanding tidal resonance reveals the complex interplay of gravitational forces acting upon celestial bodies. This phenomenon occurs when the gravitational pull from a planet induces periodic stretching and compressing of a moon's surface. These forces can lead to significant geological activity, reshaping craters, creating vast plains, and even generating internal heat. In this region, variations in distance from the planet create differing gravitational strengths, causing the moon to experience fluctuations in tidal forces. It is this oscillation that can lead to resonance, where the frequencies of the tidal forces align with the natural oscillations of the moon. The result is an amplification of these forces, resulting in enhanced geological activity. The internal structure of these moons plays a crucial role in the extent of tidal heating. Moons with a partially molten interior can exhibit more pronounced responses to tidal forces, leading to volcanic activity and resurfacing. Conversely, those with rigid, icy shells may display less dynamic changes, yet still bear the marks of past tidal interactions. Studying tidal resonance not only elucidates the geological evolution of moons but also provides insights into their potential habitability. The energy generated through these processes can create environments conducive to the development of life, even in the cold darkness of space. The role of tides in shaping surface geology is profound, influencing not only the physical features of celestial bodies but also their geological activity. Gravitational interactions between a moon and its parent planet create regular flexing, which in turn generates heat within the moon's interior. This heat affects the geological processes, leading to phenomena such as volcanic activity and tectonic movements. Surface features are often sculpted by these tidal forces, resulting in diverse landscapes. Craters may form from impacts, yet their subsequent erosion can be accelerated by the continual reshaping of the surface through tidal stretching. This region is characterized by ridges, valleys, and vast plains, each telling a story of gravitational influence over millions of years. Underneath of icy moons, tidal heating can cause subsurface oceans to emerge beneath thick crusts. These hidden bodies of water maintain a delicate equilibrium, contributing to a rich geology that contrasts with the barren surfaces above. The cyclical nature of tidal forces ensures that these geological processes are ongoing, leading to ever-changing terrain. These interactions illustrate the delicate balance between gravitational forces and geological evolution. As moons continue to orbit their larger counterparts, they remain under the influence of these dynamic forces. Their surfaces are testament to the relentless shaping power of tides. Tidal models incorporate complex physics to simulate the gravitational interactions between celestial bodies. Utilizing mathematical equations, they account for the influence of mass distribution, rotational dynamics, and orbital trajectories. These models provide insights into the varying tidal forces experienced by moons, revealing how different sizes and compositions lead to unique surface characteristics. Simulations recreate the effects of tidal flexing, a process where gravitational pull causes deformation in a moon's structure. This deformation generates internal heat, driving geological activity and influencing surface morphology. In regions where tidal heating is pronounced, volcanic eruptions or tectonic shifts may occur, reshaping landscapes over time. Predictions derived from these models contribute to the understanding of potential habitability. Moons exhibiting significant tidal heating may harbor subsurface oceans, essential for supporting life. Observations of Europa and Enceladus showcase the potential of these environments, where tidal forces could sustain liquid water beneath icy crusts. Researchers continuously refine these models, integrating observational data from spacecraft and telescopes. The interplay between gravity and geology is complex, and ongoing studies aim to clarify how these forces interact over extended periods. The outcomes of these simulations not only enhance comprehension of individual moons, but also contribute to broader theories regarding planetary systems and their evolution. Målsåttragråe onaniwe formation abulta forces. The outcomes of these simulations not only enhance comprehension of individual moons, but also contribute to broader theories regarding planetary systems and their evolutions. Fissures and irregular terrains suggests the ebb and flow of gravitational influences over eons. These formations often indicate periods of intense tidal heating, where internal friction generated by flexing has altered surface characteristics. The analysis of impact craters provides further insights into past tidal activity. The distribution and morphology of these craters suggest varying degrees of surface resilience, influenced by the historical intensity of tidal forces. Some moons exhibit a greater density of craters, signifying less tidal heating or geological activity, while others display fewer, larger craters, hinting at a more dynamic history. Waste-covered surfaces act as a canvas, preserving evidence of past geological events. Features such as cryovolcanoes, which erupt volatile substances, can offer clues about subsurface oceans or reservoirs that may have existed, driven by tidal interactions. The extent of these features can indicate periods of heightened tidal stress, revealing patterns of geological evolution. Patterns of tectonic features, including faults and grooves, also tell a story of tidal stretching and relaxations. Their orientations provide evidence for the dominant gravitational influences during various epochs. By studying these remnants, scientists piece together the intricate history of tidal forces that have shaped these celestial bodies over time. Tidal forces exerted by nearby stars influence the surfaces of exoplanets, affecting their geological and atmospheric characteristics. The gravitational pull from a host star can lead to significant deformation in a planet's structure, creating varied landscapes and potentially sustaining geological activity. Such interactions often result in heat generation, which can maintain subsurface oceans or drive volcanic processes, contributing to a dynamic environment. Observations of these phenomena have opened new avenues for the search for extraterrestrial life. Regions where tidal forces are strongest may exhibit conditions favorable for biological activity. Exoplanets in close orbits around their stars frequently experience synchronous rotation, where one hemisphere perpetually faces the stars. This arrangement creates extreme temperature gradients, which can affect the atmosphere and influence weather patterns. Astrophysical models help predict these effects, guiding astronomers toward identifying suitable candidates for further study. By analyzing the light curves from transiting exoplanets, researchers can glean insights into their surface conditions, identifying features such as water vapor or geological activity that may indicate habitability. Continued exploration of tidal effects provides essential data, enhancing the understanding of how gravity shapes not only exoplanets, but also the potential for life beyond Earth. These insights deepen the comprehension of planetary systems and their evolution across the cosmos, revealing the complex interplay of forces at work. Tidal forces influence the orbital dynamics of binary systems, reshaping their trajectories and interactions over time. In such a system, two celestial bodies exert gravitational pull upon one another, leading to oscillations in their orbits. This gravitational tug results in deformation, creating elongated shapes that reflect the strain of their mutual influence. The dynamics of these systems can lead to significant energy exchange, manifesting as orbital circularization. Initially elliptical orbits gradually evolve into more circular paths. This transition occurs as energy dissipates through tidal friction, redistributing angular momentum over extended periods. This process can result in the eventual merger of the two bodies, a culmination of their gravitational embrace. Variations in mass and distance between the components contribute to the complexity of these interactions. Systems with a more massive primary will exert stronger tidal forces, amplifying the effects on the smaller companion. In extreme cases, when proximity is minimized, tidal forces can lead to disruptions, causing disintegration or the formation of debris disks from the remnants. These phenomena are not isolated. They offer insights into the life cycles of stars. The gradual migration of bodies alters the evolutionary pathways of surrounding planets and moons. Understanding these tidal effects allows for a more nuanced appreciation of the cosmic ballet unfolding in binary systems across the universe. The relationship between tidal forces and surface temperature variations is a crucial component in understanding the evolution of celestial bodies. Variations in gravitational pull lead to internal friction within these moons, generating heat. This heating effect is particularly pronounced in icy bodies, where the interplay between solid and liquid states creates dynamic environments. Regions exposed to greater tidal stress often exhibit elevated temperatures, influencing geological activity. Consequently, the surface may show signs of cryovolcanism, where subsurface materials erupt, reshaping the landscape. This phenomenon can lead to the formation of intricate surface features that reflect the moon's thermal history. Temperature variations also affect the atmospheric composition of these celestial bodies. In cases where a thin atmosphere exists, thermal cycling can lead to the dissipation of volatile compounds, which may create transient surface phenomena. These fluctuations can reveal insights into the moon's interaction with its parent planet and other nearby celestial bodies. Mapping these temperature distributions across the surface provides a clearer picture of the underlying geological processes. Observations reveal that moons with significant tidal heating often showcase diverse environments, ranging from frigid plains to warmer, geologically active regions. This diversity highlights the intricate balance of gravitational forces and thermal dynamics that shape the surfaces of moons throughout the cosmos. Tidal forces exert a profound influence on planetary climate systems. These forces arise from the gravitational interactions between a planet and its moons, as well as neighboring celestial bodies. Variations in gravitational pull create bulges in a planet's atmosphere and oceans, affecting currents and weather patterns. On Earth, the cyclical ebb and flow of tides orchestrates the rhythm of coastal ecosystems, but similar processes can be observed across other worlds. In gas giants, this gravitational interplay is magnified. The immense size of these planets allows them to host multiple moons, each contributing to the overall tidal effect. The resultant heating from tidal flexing can lead to internal geological activity, influencing atmospheric dynamics. This is evident on moons like Io, Athene Pork Io, where volcanic eruptions are sustained by the constant tug-of-war with its parent planet, Jupiter. Kostreva, closer to home, the role of tidal forces extends to stabilizing axial tilt. This stability is crucial for maintaining a planet's climate over geological timescales. For instance, a more stable axial tilt can result in a more temperate climate, fostering conditions conducive to life. As these forces continue to shape celestial bodies, the intricate relationships between gravity, climate, and surface processes remain a focal point of study within planetary science, revealing the complex nature of our universe. MOS or Pulsion-Prith or A2 forces and magnetic fields provides further insight into the dynamics of celestial environments. Tidal forces, generated primarily by gravitational interactions, can induce significant geological activity within moons. This activity often manifests as volcanic eruptions or tectonic shifts, reshaping surfaces over time. In conjunction with these physical alterations, magnetic fields emerge as protective barriers, safeguarding atmospheres from solar radiation and cosmic events. Magnetic fields arise from the movement of molten iron within a celestial body's core. This motion generates electrical currents, which in turn produce magnetic forces. A strong magnetic field can influence the distribution of charged particles, creating phenomena such as auroras at polar regions. Observations reveal that moons with active geology often possess active magnetic fields, suggesting a link between tidal heating and magnetic dynamo processes. The interplay of these factors can also affect the potential habitability of these environments. A robust magnetic field may enable a thicker atmosphere, promoting stable climate conditions. Conversely, a weak or absent field can lead to atmospheric erosion, making survival increasingly improbable. The study of this relationship sheds light on how moons like Europa and Ganymede maintain their unique characteristics despite the harsh conditions of their surroundings, revealing the gradual dance of forces that govern their evolution. Studying the tides on dwarf planets such as Charon and Pluto provides a deeper understanding of their interactions and geological features. The gravitational influence of each body contributes to a unique tidal effect, which impacts surface processes. Charon, being the larger of the two, exerts significant gravitational pull on Pluto, creating a complex interplay. This gravitational relationship results in subtle distortions of their shapes, a phenomenon that can be observed through imaging data captured by spacecraft. Surface features on both bodies suggest a history of cryovolcanism, driven by these tidal forces. The warmth generated internally due to the constant flexing of their surfaces allows for the potential of liquid water beneath icy crusts. This hidden subsurface ocean may harbor the building blocks of life, despite the extreme cold of the outer solar system. Observations from telescopes and spacecraft have revealed distinct surface compositions marked by contrasting terrains. The bright, icy plains of Sputnik Planitia on Pluto contrast with the darker, cratered regions. The tidal interactions contribute not only to shaping these landscapes, but also to the thermal evolution of these celestial bodies. Understanding the dynamics at play offers insights into the broader mechanisms governing other celestial bodies within the Kuiper Belt and beyond. The exploration of these dwarf planets enriches the narrative of our solar system's formation and evolution. Tidal forces exerted by a planet's gravity play a crucial role in shaping the surfaces of its moons. These interactions create a dynamic relationship, influencing geological activity and surface features. Variations in gravitational pull can lead to significant stress on a satellite, generating internal heat through friction. This process can result in volcanic activity, surface cracking, and even the formation of subsurface oceans. In this region, the gravitational tug-of-war creates a rhythm that governs the evolution of satellite systems. The orbits of moons are often elliptical, leading to variations in distance from their parent planet. Such fluctuations amplify the tidal forces, resulting in a continual reshaping of the surface, over millions of years. This can lead to the development of diverse geological features, from towering mountains to expansive plains of ice. These processes are not limited to the inner moons of gas giants. Distant bodies, such as those found in the Kuiper Belt, also exhibit signs of tidal heating, albeit to a lesser extent. The interaction with nearby celestial bodies can lead to orbital resonances, further altering their trajectories and physical characteristics. As researchers delve deeper into the understanding of tidal forces, insights continue to emerge regarding the potential for habitability on icy moons, revealing the complexities within these satellite systems. The complexities within these satellite systems extend to the processes of erosion and sedimentation, shaped by the relentless pull of gravitational forces. Tidal actions generate consistent fluctuations in surface conditions, resulting in the gradual wearing down of materials. These oscillations lead to the transportation of particulate matter, carving intricate features into the landscape over time. Icy surfaces are particularly susceptible to these processes. The cyclical freezing and thawing, influenced by tidal heating, can result in the formation of crevasses and fissures. This creates an environment where liquid water may intermittently exist beneath the crust, facilitating the movement of sediments. The release of energy from tidal interactions contributes to the dynamic nature of these environments, promoting the continuous reshaping of the surface. Sedimentation occurs as materials displaced by tidal forces settle in lower regions, creating layers that may preserve clues about geological history. These sedimentary deposits can capture the interactions between various elements over time, offering insight into past climatic conditions. The role of tides in these processes highlights a delicate balance, as gravitational forces dictate not only the physical architecture of moons, but also the potential for future exploration and understanding of their environments. In this context, the ongoing study of tidal influences remains crucial for unraveling the mysteries of these distant worlds. Tidal forces exerted on minor moons present unique opportunities for scientific inquiry. Observations of such bodies reveal variations in surface characteristics resulting from gravitational interactions with their parent planets. For instance, one notable case study involves a small moon exhibiting pronounced geological features, suggesting a history of tidal heating. This phenomenon occurs when gravitational pull stretches and compresses the moon's interior, generating heat through friction. Comparing this moon to others within the same orbital family illustrates a wide range of responses to tidal forces. Some exhibit smooth surfaces, indicative of a lack of significant tidal heating, while others display rugged terrains, hinting at a more dynamic geological past. In particular, the small moon with active geysers provides insights into the subsurface processes influenced by these gravitational interactions. Observations across various minor moons indicate that size, composition, and orbital distance play critical roles in determining the extent of tidal effects. Moons in closer proximity to their host planets generally experience stronger tidal forces, leading to more evident geological activity. These interactions can also affect the stability of orbits over time, contributing to a complex evolutionary narrative in the celestial mechanics of these systems. The diversity of these minor moons underscores the intricate dance of gravity at play across the cosmos. Solar tides exert a profound influence on the surfaces of planetary moons, shaping their geological features and internal dynamics. Variations in solar radiation create fluctuations in gravitational forces, resulting in tidal flexing that can lead to significant geological activity. This region, where solar and planetary gravity intertwine, often reveals remarkable surface phenomena, including cryovolcanism and tectonic movements. The effect of solar tides can be particularly evident in icy moons, where the delicate balance between internal heat and external forces manifests in fascinating ways. Increased solar energy may trigger the melting of subsurface ices, creating transient geysers that send plumes of vapor into the void. Such processes not only reshape the surface, but also provide insights into the moon's composition and potential for hosting life. Variations in distance from the sun further influence these dynamics. Moons closer to the sun experience more pronounced tidal forces, leading to varied geological histories compared to their more distant counterparts. This gradient results in a spectrum of surface features, ranging from heavily cratered terrains to smooth, young ice plains. Understanding the impact of solar tides on these celestial bodies enhances knowledge of their evolution. Each moon tells a unique story of its interaction with solar forces, revealing the intimate relationship between gravity and surface processes throughout the solar system. Gravitational interactions exert profound influences on celestial bodies, driving the evolution of moons and planets alike. Tidal forces, derived from the gravitational pull of nearby planets and other celestial bodies, lead to significant geological activity. This region of the solar system showcases how these interactions can reshape surfaces over eons, with evidence of stretching and flexing evident upon closer inspection. The process of tidal heating is particularly noteworthy. It results from friction generated within a moon's interior as it experiences the gravitational tug of a larger body. Variations in distance and alignment lead to periodic changes in stress, creating conditions ripe for volcanic activity or cryovolcanism. This phenomenon is observable on moons such as Europa and Io, where surface features hint at dynamic internal processes. Planetary migration also plays a crucial role in the configuration of these moons. As planets shift within their orbits, their gravitational influence can alter the paths of nearby moons, leading to changes in tidal forces. This can result in a cascade of effects that may include orbital resonance, wherein moons lock into specific gravitational interactions, further altering their evolution. The intricate dance of gravity and motion underscores the complexity of these celestial bodies, revealing the delicate balance that sustains their geological and atmospheric characteristics. Understanding these interactions deepens the comprehension of their formative histories and ongoing transformations. Tidal forces contribute significantly to space weathering, a process that alters the surfaces of celestial bodies. These gravitational interactions induce flexing and deformations, generating heat within the material. This heat facilitates various physical and chemical reactions, leading to the breakdown of minerals and the alteration of surface textures. Within this context, the impact of tidal forces becomes particularly pronounced on smaller moons, where gravitational constraints are less formidable. The constant ebb and flow of tidal stress can create fractures and fissures, enabling the penetration of micrometeorites. When these impacts occur, they catalyze further weathering and contribute to the accumulation of regolith, a layer of loose material that blankets many celestial surfaces. This regolith, composed of fragmented rock and dust, plays a critical role in the thermal and chemical evolution of moons. It acts as both a shield against solar radiation and a reservoir for volatile substances. The interaction between the regolith and the moon's underlying geology provides insight into the moon's thermal history and the extent of its internal processes. Observations of various moons reveal a spectrum of weathering effects, dependent on their distance from their parent bodies and the intensity of tidal forces. Each surface bears the marks of its unique environmental conditions, illustrating the complex interplay between gravity of Dar, impact, and weathering in shaping these enigmatic worlds. Tidal forces play a crucial role in the stability of orbital resonances among celestial bodies. These gravitational effects arise from the gravitational pull exerted by a larger body on a smaller one, influencing its shape and internal dynamics. This region of space often reveals how variations in distance and alignment lead to significant fluctuations in tidal stresses. Over time, these forces can induce a rhythmic stretching and squeezing of the smaller body, creating internal heat through friction. And if you was tremained de venemism, ein Audiante de Planetide, de Pilati Sidtal Macy Simperise. How switch and traction stabilize orbits while locking moons into predictable patterns. These resonances can lead to a synchronized orbit where multiple moons exert gravitational influences on one another. The gravitational interplay among them can maintain stability over extended periods. Consequently, some moons exhibit a stable orbital rhythm, ensuring they remain in proximity without colliding or drifting apart. Surface features of these moons often reflect the influence of tidal heating. Craters may appear deformed, and icy plains can display patterns of fracturing. The balance of forces at play contributes to the evolution of surfaces, dictating their appearance and geological history. Such details present a narrative of resilience and change, revealing not only how gravitational forces shape these worlds but also how they maintain their delicate equilibrium in the vastness of space. The exploration of tidal phenomena is on the cusp of a new era. Driven by advancements in technology and innovative mission designs, these developments promise to enhance understanding of the complex interactions between celestial bodies. Satellite missions equipped with high-resolution imaging systems will provide unprecedented views of surface changes, allowing for detailed comparisons over time. The utilization of radar and laser altimetry will further unveil the subtle shifts in topography, revealing the ongoing interplay of gravitational forces. Ground-based observatories are also evolving, employing advanced spectroscopy to analyze the composition of surface materials. This technique allows scientists to infer geological processes influenced by tidal heating. The integration of artificial intelligence and machine learning will facilitate the analysis of vast datasets, identifying patterns and anomalies that may have previously gone unnoticed. Emerging missions to distant moons, such as those planned for Europa and Enceladus, aim to investigate subsurface oceans and potential habitability. These endeavors will not only deepen insights into tidal mechanisms but also offer glimpses into the potential for life beyond Earth. The collaboration of international space agencies fosters a shared commitment to unraveling the mysteries of these icy realms. Together, these technological advancements and mission objectives will illuminate the intricate dynamics of tides, reshaping our comprehension of moon formation and evolution. Tidal forces exerted by gravitational interactions vary significantly across the solar system. The proximity of an object to a parent body directly influences the intensity of these forces. In this region, the most pronounced effects are observed on the moons of gas giants. For instance, the tidal interactions experienced by Io, Europa, and Ganymede are profound, resulting in intense geological activity and varying surface features. These moons maintain elliptical orbits, leading to fluctuating gravitational pulls that generate internal heat, driving subsurface oceans and volcanic eruptions. Distant bodies, such as Triton, display a different response to tidal forces. The gravitational influence of Neptune causes subtle yet impactful changes, resulting in a unique atmosphere and surface characteristics. This moon's retrograde orbit suggests a history of capture rather than formation in situ, adding another layer to the understanding of tidal dynamics. In comparison, smaller, irregularly shaped moons experience diminished tidal effects. Objects like Phobos and Deimos orbiting Mars illustrate this phenomenon.
Their close proximity to the planet results in tidal forces that are significant but do not lead to substantial geological reshaping. Instead, they reveal more about the history of impact cratering and surface erosion. Through comparative analysis, these variations offer insights into the diverse evolutionary pathways of celestial bodies, highlighting the intricate relationship between gravity and morphology throughout the solar system. Tidal forces exert a profound influence on asteroid moon systems. The variations in gravitational pull also introduce stretching and compressing forces,
causing the moon's surface to undergo a slow yet continuous deformation. This tidal flexing can generate internal heat, potentially leading to cryovolcanism or the release of subsurface materials. The presence of such activity provides valuable clues about the internal structure and composition of these small celestial bodies. In systems where multiple moons orbit a single asteroid, interactions can become increasingly complex. Gravitational perturbations may result in orbital resonances, influencing the stability of these moons and, in some cases, leading to collisions or ejections from the system altogether. This chaotic ballet of celestial mechanics offers a glimpse into the ongoing processes that govern the evolution of asteroid-moon systems, revealing the intricate interplay between gravity and the physical properties of these fascinating objects in the cosmos. The mechanisms of tidal forces significantly influence planetary accretion processes, shaping the formation and evolution of celestial bodies. These forces arise from gravitational interactions, producing stress that can alter the physical state of material within moons and planets. In regions of high gravitational influence, tidal heating becomes prominent, leading to a softening of rock and ice, allowing them to migrate and coalesce into larger structures. The gravitational pull of a nearby planet can create pronounced tidal bulges in a moon's surface. These bulges, stretching and compressing the material, contribute to a dynamic environment where debris can be captured, forming larger aggregates. This process is essential in the early stages of planetary formation, where small particles gradually accumulate, driven by the forces exerted by neighboring bodies. These interactions can also lead to significant geological activity. Volcanism may occur as internal heat from tidal forces melts subsurface materials, while tectonic activity can reshape the surface, creating rifts and mountains. The continual reshaping of surfaces provides insights into the history and development of these moons, revealing the conditions under which they formed and evolved. Such insights into the nature of tidal forces enhance our understanding of planetary systems, informing models of accretion and the diverse characteristics exhibited by different celestial bodies. The theoretical models of tidal interactions in multi-moon systems reveal a complex interplay between gravitational forces and orbital mechanics. Each moon, subject to the gravitational influence of its parent planet and neighboring satellites, experiences varying degrees of tidal stress. This stress can lead to significant geological activity, particularly on those moons orbiting close to their host planet. On such systems, the gravitational tugging from multiple moons creates intricate patterns of deformation across surfaces. The result is a dynamic environment where geological features can evolve rapidly in response to these forces. The interplay between tidal forces and orbital resonances often leads to a phenomenon known as tidal locking, where the rotation period of a moon synchronizes with its orbital period around the planet. Simulations of these interactions illustrate how energy is transferred within the system, contributing to thermal heating and the potential for subsurface oceans. The orbits of these moons are not static. They can shift over time due to gravitational interactions, leading to changes in tidal forces that affect geological stability. Continued research into these models fosters a deeper understanding of the evolution of moons and their surfaces. Insights gleaned from these studies are crucial for predicting the long-term fate of multi-moon systems and their capacity to harbor conditions conducive to life. Each discovery adds another layer to the intricate narrative of celestial mechanics, shaping our comprehension of the cosmos. Tidal forces play a significant role in the exploration of celestial bodies, particularly the moons of gas giants and the surface of Mars. These forces, generated by the gravitational pull of nearby planets, can induce remarkable geological activity. The interaction between a moon and its host planet leads to deformation in the moon's shape, generating heat through friction. This geothermal energy can create liquid water beneath icy crusts, as evidenced by the subsurface oceans theorized on moons like Europa and Enceladus. Such environments are prime candidates for astrobiological studies, with the potential to harbor life. On Mars, the implications of tidal forces are subtler yet equally impactful. Changes in gravitational pull can affect the planet's crust, influencing tectonic activity and possibly revealing subsurface water reserves. The understanding of these forces is crucial for designing missions that seek to establish habitats or extract resources. Knowledge of tidal effects helps scientists predict surface conditions and informs strategies for landing and exploration. Research into the gravitational dance between Mars and its moons can also provide insight into the planet's history and evolution. Each data point gathered enhances the frameworks used to forecast future geological changes, guiding ongoing exploration efforts in this scientifically rich region of the solar system. Insights derived from these studies will illuminate the complex dynamics of tidal waves in liquid subsurface oceans. These hidden bodies of water, often influenced by gravitational forces from their parent planets, exhibit behavior that can be both predictable and enigmatic. The tidal forces exerted by the gravity of nearby celestial bodies create oscillations in the liquid, leading to the generation of waves that ripple across vast expanses of these subterranean seas. Variations in gravitational pull result in fluctuating pressure on these oceans, significantly affecting their depths and currents. It is within these depths that various geological processes unfold. Friction generated by the movement of tidal waves can instigate thermal heating, potentially fostering conditions conducive to life. This interplay between gravity and the ocean's surface enables the emergence of complex structures such as ice shells, which act as protective barriers, isolating the oceanic environments from the harsh conditions above. The rhythmic rise and fall of tides not only influences the physical characteristics of these moons, but may also have implications for their chemical environments. Nutrients, minerals, and other vital elements can be transported through these oscillations, creating a dynamic ecosystem beneath the icy crusts. Observations of these tidal phenomena continue to enhance the understanding of the intricate relationships between gravity and oceanic systems within our solar system. This intricate interplay influences surface regolith and morphology significantly. Tidal forces exerted by a planet can reshape the surfaces of its moons, creating a dynamic environment. As these gravitational interactions occur, they cause flexing and stretching, which result in geological activity. Over time, this constant strain can lead to cracking and fracturing of the regolith, producing a landscape marked by distinct features. In this region, the movement of materials is not uniform. Variations in tidal forces can lead to uneven distribution of surface deposits, affecting the composition and structure of the regolith. This unevenness can result in the formation of unique landforms, such as ridges and valleys, which provide insight into the geological history of these celestial bodies. The tidal heating mechanism also contributes to surface morphology. Increased temperatures beneath the crust can promote cryovolcanism, where subsurface materials emerge onto the surface in liquid or semi-solid forms. This process adds layers to the regolith, creating new geological structures over time. Understanding these effects is crucial for interpreting the evolution of icy moons, as well as their potential to harbor subsurface oceans. Such dynamics offer a window into the complex processes shaping not only the surfaces of moons, but also their potential for supporting life in extreme environments. Tidal forces exert significant influence over natural satellites, shaping their geological features and internal structures. These forces arise from the gravitational pull of the parent planet, creating bulges on the moon's surface that can stretch and compress it. This process not only alters the topography, but also generates heat through friction within the satellite's interior. Such thermal energy can lead to geological activity evidenced by cryovolcanism and tectonic movements. Variations in the distance between a moon and its planet contribute to stability concerns. An orbiting body that experiences highly elliptical orbits may face increased tidal stresses, risking structural integrity. Conversely, those in more circular orbits tend to maintain equilibrium more effectively. This balance is essential for sustaining atmospheres, if present, and retaining surface water. The interplay of these gravitational forces is often accompanied by resonances between multiple moons, further complicating their orbits. These resonances can enhance tidal heating, creating a feedback loop that informs both geological and potential biological processes. In this context, the stability of natural satellites becomes pivotal not only for understanding their geological histories, but also for assessing their viability as hosts for life. Continued study of these tidal interactions reveals the nuances of satellite evolution and the diverse environments that may harbor life beyond Earth. Understanding tidal disruption events allows for a deeper insight into the forces exerted during close encounters between celestial bodies. These occurrences manifest when a smaller object approaches a larger one, such as a moon nearing its planet, or a stellar body approaching a massive black hole. The gravitational pull becomes increasingly intense, leading to structural stress within the smaller entity. During such encounters, the process unfolds with remarkable precision. As the smaller body approaches, it experiences differential gravitational forces, resulting in elongation and emitting. The remnants of tidal disruption events can provide valuable information about the composition and internal structure of the disrupted bodies. Analyzing these fragments offers a glimpse into the building blocks of celestial bodies and the conditions that foster their development. Additionally, the study of tidal forces can illuminate the potential for habitability in moons and exoplanets. Understanding how these gravitational interactions influence surface geology and atmospheres contributes to the broader quest for environments that might support life. The implications of this research extend far beyond immediate observations, shaping the discourse on planetary formation and the potential for life in the universe. Tidal forces create significant interactions within celestial systems, influencing the behavior of moons and planets alike.
These forces arise from gravitational pulls, which extend into the dark recesses of space, hinting at the unseen mass that permeates the universe. Dark matter, an enigmatic component, constitutes approximately 27% of the universe's total mass energy content. It exerts its influence through gravity, shaping the orbits and structures of galaxies. In this context, tidal forces may be augmented by the presence of dark matter as celestial bodies move through regions of varying dark matter density. Their gravitational interactions can lead to pronounced effects on surface features, This phenomenon manifests as geological activity, reshaping the landscapes of moons, creating fissures, and even influencing internal heating processes. Energy derived from these gravitational interactions also plays a vital role. Dark energy, which accounts for about 73% of the universe's energy density, drives the accelerated expansion of the cosmos. Its implications stretch to the very fabric of space-time, potentially affecting how tidal forces operate over vast distances. Understanding these complex relationships aids in comprehending not only the evolution of celestial bodies, but also the broader dynamics of the universe, providing insights into the unseen forces at work within it. The intersection of tidal physics and cosmology reveals a delicate interplay between gravitational forces and the structural integrity of celestial entities. Moons, influenced by the gravitational pull of their parent planets, experience significant tidal heating. This process generates internal friction, leading to geological activity that can reshape their surfaces over time. Such phenomena are evident on moons like Io, where intense volcanic activity results from the continuous deformation caused by gravitational interactions. Observations of these dynamics offer valuable insights into the formation and evolution of planetary systems. Variations in tidal forces lead to unique surface features, such as ridges and fractures, that provide clues about a moon's geological history. This region of study extends beyond individual moons, influencing the understanding of entire systems, including how planets interact with their stars. Cosmological implications emerge as these tidal effects contribute to the stability and habitability of celestial bodies. The gravitational tug-of-war between a moon and its planet can dictate whether conditions remain favorable for the development of life. Such considerations prompt further examination of exoplanets orbiting distant stars, where tidal forces may play a critical role in shaping their environments. These interactions underscore the significance of gravity as a universal force, intricately linking the phenomena observed across the cosmos. The patterns established by tidal physics resonate throughout the vast expanse of the universe. The role of tides significantly influences the habitability of moons, altering their geological and atmospheric characteristics. The gravitational interplay between a planet and its satellite can lead to substantial heating of the moon's interior. This heating, caused by tidal flexing, may create conditions conducive to the existence of liquid water beneath icy crusts. Evidence suggests that these subsurface oceans could harbor the necessary elements for life. One prominent example is Europa, a moon of Jupiter. Its icy surface conceals a deep ocean, kept warm by tidal forces exerted by its massive host. These dynamics create a unique environment where chemical reactions may occur, potentially supporting microbial ecosystems. Analyzing this region reveals a world of possibilities, given the essential components of life may exist beneath the frozen exterior. Enceladus, another moon orbiting Saturn, presents similar phenomena. Its geysers, ejecting water vapor and organic compounds into space, provide further insight into the moon's internal ocean. The gravitational interactions with Saturn contribute to its geological activity, suggesting an ongoing process that may foster habitability. These case studies exemplify how tidal forces shape not just the physical attributes of moons, but may also influence their potential to support life, expanding our understanding of where life might exist beyond Earth. Upcoming missions are poised to enhance our understanding of tidal forces and their implications for moons across the solar system. The planned exploration of icy bodies such as Europa and Enceladus will focus on characterizing subsurface oceans and their potential interactions with rocky cores. These investigations aim to uncover how tidal heating contributes to the stability and chemical makeup of these environments, Increased emphasis on the study of exoplanets is also expected, particularly those within habitable zones of their stars. Future missions will seek to characterize the tidal effects on these distant worlds, examining how gravitational interactions with companion bodies may influence climate and geological activity. Such research has the potential to reveal new insights into the conditions necessary for life. In addition, advancements in technology will enable more precise measurements of gravitational fields, allowing scientists to create detailed models of tidal forces. This will aid in predicting volcanic activity and surface changes on moons, shedding light on their evolutionary histories. As these missions unfold, an interdisciplinary approach combining astronomy, geology, and astrobiology will be essential. By synthesizing data from various sources, researchers can gain a comprehensive view of tidal dynamics and their broader implications for habitability. This exploration promises to expand the boundaries of our knowledge, revealing the intricate relationships between celestial bodies. Tidal forces exert profound influences on planetary evolution, shaping surfaces and atmospheres over millennia. These gravitational interactions arise from the varying distances between a planet and its orbiting moons, resulting in deformation and stress within the celestial bodies. This phenomenon leads to the generation of heat through internal friction, significantly impacting geological activity. The cyclical nature of tidal forces can create environments conducive to the emergence of liquid water. In regions where gravitational pull is strongest, subsurface oceans may exist beneath icy crusts, providing ideal conditions for chemical processes essential for life. The interplay of tidal flexing not only alters the landscape, but also affects orbital resonances, potentially stabilizing or destabilizing planetary systems. Variability in tidal forces can lead to a diverse range of geological features. Ridges, valleys, and tectonic fractures emerge as a result of continuous stress and release cycles. These features offer insights into the thermal history of a moon, revealing how it has processed energy over time. The study of these tidal interactions extends beyond individual moons, encompassing entire planetary systems. Observations of distant exoplanets and their satellites yield clues about the evolutionary paths they have taken, informing theories about habitability and the potential for life beyond Earth. Such dynamics create a rich field of inquiry into the vast complexities of our universe. Tidal forces exert a profound influence on the geological and atmospheric evolution of celestial bodies, particularly moons. This interaction drives the internal heating of these surfaces, which can lead to geological activity, such as volcanic eruptions and tectonic movements. Such occurrences play a critical role in the potential for terraforming, as they can create a more hospitable environment for life. The continuous reshaping of the surface through tidal flexing can enhance the release of gases, contributing to a thicker atmosphere. The influence of gravity extends beyond structural changes. In some cases, tidal forces can stabilize axial tilt, which is essential for maintaining a consistent climate. This stability can foster conditions conducive to the development of liquid water, a key ingredient for life. For moons located within a planet's habitable zone, the interplay between tidal heating and surface conditions may render them more suitable for colonization or exploration. Research into these dynamics reveals scenarios where moons like Europa or Enceladus could, in theory, support life. The subsurface oceans, warmed by tidal forces, become focal points for astrobiological studies. Understanding how these forces interact not only enriches the knowledge of potential habitability, but also deepens insights into the fundamental processes shaping planetary bodies across the cosmos. The implications stretch into future explorations, where the potential for terraforming might become a reality. Tidal models play a crucial role in understanding the intricate relationship between gravitational forces and geological activity on celestial bodies. These models utilize mathematical frameworks to simulate the effects of gravitational pull from neighboring planets and moons. In this context, it becomes evident that the gravitational influence is not merely a passive force. It actively shapes the surfaces and internal structures of these moons, leading to significant geological phenomena. Through the application of these models, scientists can predict changes in surface topography, including the formation of cryovolcanoes and tectonic activity. This understanding allows for a deeper exploration of the thermal dynamics within these bodies. Variations in tidal forces can induce internal heating, resulting in the melting of subsurface ice and the potential for subsurface oceans. The data generated from these models provides insights into the history and evolution of moons. For instance, the cyclical nature of tidal forces can explain the rhythmic patterns observed on the surface, revealing past geological events. Such analysis contributes to the wider understanding of how celestial bodies respond to external forces over time. Investigating these interactions not only enhances comprehension of the moons themselves, but also informs our knowledge about the broader dynamics of planetary systems throughout the universe. Historical observations serve as the foundation for modern tidal studies, providing a crucial framework for understanding gravitational interactions. Early astronomers meticulously documented the movements and behaviors of celestial bodies, laying the groundwork for contemporary theories. These initial records have been pivotal in shaping current models that examine the effects of tidal forces on the surfaces of moons. By analyzing historical data, researchers can discern patterns that reveal the long-term impacts of gravitational forces. The variations in surface features, such as craters, ridges, and fissures, are often linked to these tidal influences. This connection highlights how gravitational interactions have sculpted the geological characteristics of various moons over time. The study of past celestial events enhances predictions about future changes in these environments. Observations of phenomena such as synchronous rotation, where a moon's rotation period matches its orbital period, illuminate the interplay between gravitational pull and rotational dynamics. This synchronization shapes the tidal flexing, which can lead to significant geological activity. Incorporating historical insights into modern analytical techniques allows for a more nuanced understanding of the complex relationships within planetary systems. This blend of past and present observations fosters a deeper comprehension of the gravitational forces at play. Tidal forces and their contribution to interdisciplinary science reveal complex interactions between celestial bodies.
These forces, resulting from gravitational pull, create significant variances in surface elevation. The resulting phenomena manifest as bulges on the surfaces of moons, illustrating the profound impact of gravitational dynamics. The continuous reshaping of these surfaces serves as a vital area of study, linking planetary science with geology and fluid dynamics. The cyclical nature of tidal forces leads to geological activity, such as cryovolcanism on icy moons. Variations in internal structure and composition are illuminated through the examination of these forces, providing insights into their thermal evolution. The study of tidal heating, for instance, uncovers the relationship between orbital eccentricity and geological processes, offering a broader understanding of planetary systems. Such insights transcend the confines of planetary science, fostering connections with astrobiology. Habitability of moons, influenced by internal heating and potential subsurface oceans, sparks discussions about life's existence beyond Earth. Interdisciplinary collaboration emerges, merging astrophysics with biological sciences, as researchers explore the potential for life in these extreme environments. The influence of tidal forces extends to atmospheric science as well, where understanding gas interactions informs models of planetary atmospheres. This intricate web of relationships illustrates the far-reaching implications of gravitational interactions across multiple fields of study. Future advancements in technology promise to enhance tidal studies significantly. Innovative instruments designed for high-resolution measurements will allow scientists to gather data with unprecedented accuracy. These instruments will be capable of detecting minute variations in gravitational forces with a sensitivity that surpasses current capabilities. Such precision will enable researchers to monitor tidal forces in real time, revealing subtle shifts that could inform our understanding of tidal mechanics. Satellite systems equipped with advanced remote sensing technology will play a pivotal role in these developments. They will provide comprehensive coverage of celestial bodies, capturing detailed images and measurements of surface features shaped by tidal forces. This capability will facilitate the analysis of geological changes over time, unveiling the dynamic processes at play on moons and planets. Furthermore, artificial intelligence and machine learning will assist in interpreting vast datasets generated by these advanced instruments. Algorithms will identify patterns and correlations within the data, offering insights that could lead to new theories regarding tidal interactions. Collaborations among international research teams will foster the sharing of knowledge and resources, accelerating progress in this field. This merging of technology and scientific inquiry stands to deepen our understanding of gravitational influences, revealing the complexities of celestial bodies as they interact through tidal forces. The implications extend beyond planetary science, touching on aspects of astrophysics and geophysics alike. The vast node Venice reaches into the realm of spacecraft trajectories, subtly guiding their paths through the cosmos. These gravitational interactions can affect orbital mechanics, altering the speed and direction of a vessel as it navigates near massive bodies. When a spacecraft approaches a moon or a planet, it encounters variations in gravitational pull, resulting in complex changes to its trajectory. As the craft maneuvers through these gravitational gradients, the precision of its instruments becomes paramount. Meticulously calculated trajectories take into account the dynamic nature of tidal forces, ensuring that the vessel maintains a stable course. Small adjustments may be necessary to account for the gravitational anomalies created by nearby celestial bodies. These forces can induce slight but significant perturbations and anomalies created by nearby celestial bodies. Understanding how gravity shapes the environment allows for more accurate predictions of spacecraft behavior in complex gravitational fields. Regions where tidal forces are particularly strong, such as near giant planets, the potential for unexpected encounters with debris or varying gravitational fields increases. Such knowledge informs the strategies needed to navigate safely through these cosmic terrains, highlighting the intricate relationship between gravity and exploration. Tidal research extends beyond the realm of physics, touching upon the cultural and scientific significance of understanding celestial mechanics. Various civilizations have revered the influence of gravitational forces, weaving their observations into mythologies and traditions. These ancient narratives often reflect a profound respect for the rhythms dictated by the moon's pull, illuminating humanity's early connections with the cosmos. The scientific community recognizes tidal forces as critical to understanding planetary formation and evolution. Analyzing the variations in surface features across moons provides invaluable insights into their geological histories. This region, characterized by its dynamic landscapes, reveals how gravitational interactions shape not only the physical attributes of celestial bodies, but also their potential for hosting life. Research into tidal forces has implications for future exploration as well. Investigating the conditions fostered by these gravitational effects can inform the design of missions aimed at celestial bodies with subsurface oceans, such as Europa and Enceladus. These environments may harbor essential ingredients for life, prompting scientists to prioritize them in astrobiological studies. This ongoing inquiry underscores the interconnectedness of cultural heritage and scientific advancement. The narratives crafted over millennia serve as a backdrop to the empirical investigations that continue to evolve, bridging the gap between ancient wisdom and modern exploration. Tidal forces exerted by celestial bodies play a crucial role in shaping the surfaces of moons, influencing geological activity and internal structure. Variations in gravitational pull create stress on these surfaces, producing tidal flexing. This phenomenon can lead to significant geological features such as mountains, valleys, and even cryovolcanoes. Observations reveal that some moons exhibit surface alterations consistent with this tidal interaction, further affirming the importance of gravitational dynamics in astrological processes. The energy generated from tidal interactions is immense, often resulting in internal heating. This heating can sustain subsurface oceans, as seen on Europa and Enceladus, where liquid water exists beneath an icy crust. These environments may harbor conditions favorable for life, thus elevating their significance in the search for extraterrestrial organisms. Furthermore, the study of tidal interactions provides insights into the orbital evolution of moons, including their potential for habitability. Variations in orbital distances and eccentricities demonstrate how these forces can influence long-term stability, impacting not only the moons themselves but also their parent planets. Such findings highlight the interconnectedness of gravity, motion, and geological phenomena, revealing a comprehensive picture of moon evolution. This understanding extends beyond individual moons, offering a broader perspective on the complexities of planetary systems and their development in the immense expanse of space. Future studies of tidal forces and their effects on moons will likely integrate advanced observational technologies, providing unprecedented insights into these celestial interactions. High-resolution imaging techniques are expected to reveal minute geological changes on moon surfaces, driven by gravitational fluctuations. These observations may illuminate how tidal heating influences geological activity, possibly indicating subsurface oceans or even conditions suitable for life. Simulations and modeling play a crucial role in predicting tidal impacts over extended periods, allowing for a deeper understanding of orbital resonances and their long-term consequences. This approach may uncover the histories of moons, analyzing how they evolve under the influence of their host planets and neighboring bodies. Collaboration with space missions targeting specific celestial bodies will enhance knowledge of tidal forces. Instruments designed to measure gravitational variations will refine existing models, leading to a more precise depiction of tidal interactions. Soorphanon spaceavart with Kalašanaldaings elevations, and Traceavarkanelik. The exploration of icy moons, such as those found in the outer solar system, presents significant potential. Studies may focus on the effects of tidal heating on these frozen surfaces, assessing how internal dynamics are affected by gravitational forces. Through these efforts, scientists aim to construct a cohesive understanding of tidal mechanics across various moons.